Hello everyone, this is your course instructor Khushwant Fatnani, and I welcome you all once again to this revision course series where we are revising the syllabus in physics for JEE and NEET 2020. Let us continue with our work. I'm so happy to inform all of you that this is our final class of this entire series. Let us continue. We have completed all the chapters in class 11th and 12th except for the last one, that is semiconductors or electronic devices, the final chapter. Let us see this chapter in terms of its important concepts and some important questions. Let's go. Right? All right, class. All right. So let's start off. Let me take the blackboard and begin. Right? All right. So, class, first of all, writing here the topic, that is electronic devices, right? Electronic devices. Electronic devices, right? Let us see the important topics in this chapter. This chapter consists of several important topics like logic gates, right? You will have questions in the previous years which have been based on logic gates and related concepts. Then there are questions from the concept of transistors, right? NPN, PNP, right? Transistors. Then we also have questions from the topics like rectifiers, right? Semiconductors in general, etc. Of course, we'll have some questions based upon xenodiodes or xenodiodes, right? As you would call it, right? So this is the scenario, class. This is the scenario, right? 1 to 2 questions every year you'll find in the papers, right? 1 to 2 questions every year you'll find. Let's say when I talk about, say, JEE mains, right? When you talk about JEE mains, you will have, let's say, 1 to 2 questions every year. The same is the scenario with NEET, right? So let us start off with the questions, right? So here is the first question. So the first question we are taking is from the concept of xenodiodes, one of the most beautiful concepts, right? Because xenodiode has a very special functionality, right? Let's see this by the means of this question. So I'm starting from a recent paper. This is question from JEE 2019. So the question goes as under. It says that the reverse breakdown voltage of a Zener diode, reverse breakdown voltage of a Zener diode is given to us. For a Zener diode is given to us as, let's say, VZ 5.6 volts, 5.6 volts, right? Now, let me draw this in the form of a circuit. Here, the circuit is given to you. I draw a battery, a resistor. The resistance of this one is 2 ohms. battery has a voltage of 9 volts, or you call it the EMF. You have been shown that some current is going here in this branch, which they have labeled as IZ, right? That is, of course, the current which is going in the Zener diode, right? And here they have also shown the Zener diode. So Zener diode works in reverse bias. I hope all of us are aware with the function of a Zener diode. It is generally used as a voltage regulator. Class, remember, Zener diode is used as a voltage regulator. Voltage regulator. Irrespective of how much you vary the current, right, in the reverse bias, we see that the voltage always remains constant. Voltage remains constant. So this resistor has resistance 800 ohms, right? Now you're supposed to find out the value of IZ, that is current going through the Zener diode, this value of current. Class, this is one of the most beautiful concepts. Again, once again, I would say this is one of the most beautiful concepts because see here, it brings into application the concepts we have read in the chapter current electricity, right? Also, apart from the semiconductor concept. So class, we all will see here that we have a circuit, okay? We have a circuit. And this circuit, we can see that 5.6 is the voltage difference across the ends of the Zener diode. That means if I label this point as A and this as B, then the voltage difference between A and B is equal to 5.6 volts. Am I correct? Now, point A is same as this point and point B is same as this one. This definitely means that this 800 ohms of resistor also has a voltage of 5.6 volts across its ends. Yes, you are correct. Therefore, the current in this branch, will be given by Ohm's law. See here the application of current electricity concept. V is equal to IR, right? Therefore, we can find out I in this branch. Let us take this value of I for this particular branch. Let's say I over here is given by I naught, okay? Now, I naught value is equal to voltage difference between A and B upon resistance between A and B. You can clearly see that the resistance between A and B is 800 and the voltage is given in the question as 5.6. So I get the answer as 7 milliamperes. Am I correct? Right. So after understanding this, next step. See here, I now know the current in this branch I naught is equal to 7 milliamperes, right? I also know the voltage difference between these 2 points. Voltage difference between these 2 points, A and B. It is equal to 5.6 volts. Correct? Now class, this is where most of the students tend to get confused, and this is where we all have to actually develop our understanding. What is happening? What is happening in this circuit? See here. We actually have arrangement of the elements in the circuit in this pattern. Have a look. This is the cell. Here is the cell. This is one resistor. This is another resistor. Let us forget about the diode for some time. Because one of the principal functions of diode, see here, one of the principal functions of the diode is to maintain the voltage across this resistor, to maintain the voltage across this resistor, right? So across this resistor AB, the voltage has been maintained to a value of 5.6 volts, correct? Whereas how much voltage is available because of the battery? It is 9 volts. Let me also write down the voltage values, the resistor values. The resistance has a value 800 ohms here and 200 ohms here. Correct? What does this mean? In series, always remember that in series, tell me what happens in a series circuit. The voltage gets distributed. The voltage gets distributed, right? So if 600, if total voltage available is 9 volts, if total voltage available is 9 volts, out of which 5.6 is across 5.6 is across 800 ohms, it definitely means the rest is across 200 ohms. That is 9 minus 5.6, right? 9 minus 5 gives you a 4, and 4 minus 0.6, that is 3.4 volts, is across the 200 ohm resistor. Am I clear, class? Am I clear? Right? Now, have a look. I'll draw the Zener diode over here, just indicating the fact that this is how it is installed and applied in reverse bias, right? Now see, here is the current IZ and here is the current I naught. What does this mean? Let's say this is the junction C. If the total current in the circuit, is small I, then definitely small I is turning into IZ, or splitting into IZ and I naught, right? Now, since I know this resistor has a resistance of 200 ohms and a voltage of 3.5 volts, I can find out the current through this resistor. Am I correct, class? Yes. So we have the current through this resistor, where the resistance is 200 ohms and the voltage across its ends is 3.5 volts, is given by, again, Ohm's law, V is equal to IR, and so I is equal to V by R. Correct? So V is 3.4 whole by 200. Correct? This will give you 34 by 2 into 10 power minus 3 amperes. That is 17 milliamperes. Am I correct? Now, look at the scenario. What is happening? This is one resistor in the circuit where 17 milliamperes of current was flowing through a resistor of 200 ohms. Now some current has gone into the Zener diode branch. Rest of it has gone into the 800 ohm resistor branch. Correct? The current has got divided. So I can see that here in this branch with the Zener diode, we had assumed, or we were given in the question rather, that current is IZ. This was I, right? This current in the main branch, and here we had found that the current is 7 milliamperes. See here, I naught was 7 milliamperes. Now see, it's so evident, so clear from the question that I is equal to IZ plus I naught, and therefore Iz is equal to I minus I naught, that is 17 minus 7 milliamperes. Correct? That gives me 10 milliamperes as the answer. Am I correct, class? Am I clear? I'll repeat what I did and we will be once again fine with the question. So let us see. This was the first and this was the second page. See. So we started with a question where we were given a Zener diode voltage, Zener diode setup, right? We know that a Zener diode is used to maintain the voltage. So where is it maintaining the voltage? Across this resistor, which is connected in parallel to this Zener diode. And the resistance value is 800 ohms, right? Now, using this data, we tried to find out if the voltage across 800 ohms is same as the voltage across this Zener diode, that is 5.6. What is the value of I naught? We got that value as 7 milliamperes. After this, we know from the given question that 9 volt is the total voltage available, out of which 5.6 is across 800 ohms. Where is the rest of the voltage? In series connection. Now hide this one, right? Hide this Zener diode. Forget about it. In series connection, the voltage gets distributed and therefore 5.6 is across AB. The rest 3.4 out of 9 volts, rest 3.4 is across 200 ohms, right? Now you have the voltage across 200 ohms, so you can find out the current which is passing through this 200 ohm resistor, right? That comes out to be 17 milliamperes. 17 milliamperes. Once you get this answer, the equation is very clear because you have I is equal to Iz plus I naught, and therefore Iz value is equal to 17 minus 7, that is 10 milliamperes. Is it clear, class? Great. Very good. Now, let us take the next question. So, next, let us take this question from again, let us now take this one from NEET 2016. Right? See, the question says that you have a junction diode which is ideal in nature. You have an ideal junction diode. We all know, right, what is a junction diode? It is a PN junction, right? Now, it is given in the question. In which circuit? See, a part of the circuit is given and we have to find out the value of current through AB. Value of current passing through AB. Now, what is AB? Have a look at the diagram to get the understanding of it, right? This is the wire, this is the diode, and then here is the resistor, and then another point. This is given as A, this is B, right? And here there is a current flowing in it, which is IAB, right? There is a potential of 4 volts at A and a potential of minus 6 volts at B. You are given that the resistor has a resistance of 1 kilo ohms. 1 kilo ohms, right? And we are supposed to find out IAB. The options given to you are 10 power minus 2 amperes, then 10 power minus 1 amperes, next one 10 power minus 3 amperes, and 0 amperes. Let's see. So for this question, how will we go about it? See here, very, very simple. Again, a concept which has to be used from current electricity. Do you remember whenever we go in the direction of current, voltage decreases? Whenever we go in the direction of current, voltage decreases. So we will start from voltage at A. VA minus of I into R. Which I? Of course, the current in the circuit. This is making you reach the point B. Very simple. Therefore, VA minus VB whole by R is giving you IAB. Let us put the values. You have VA as +4, VB as -6, and R as 1000 ohms. Please mark, it is 1 kilo ohms and not 1 ohm. This is the place where we need to be super careful, right? Okay, so we have 10 upon 1000 amperes, which can also be written as 10 milliamperes, right? Or 10 power minus 2 amperes. Am I correct, class? So, which one should be your answer? The first option. Just verify this. Have you all got this answer? Check it quickly. Yes, get going. I'm waiting for all of you, right? Okay, now let us move to the next question, right? One more interesting question, class. One more interesting question. So this question, the next one which we are taking up is, tell me, should we go for a question from JEE now, right? Okay, okay, okay. So here is the question. Note it down. This is a question from IEEE 2012. All right. You need to find out the truth table. I'm not drawing all the truth tables, but I'll give you the circuit. Okay. So here is the circuit. You have NAND gates given, okay? The NAND gates are given in this pattern. Have a look. This is one. Here is the second one. Here is the third one, right? Here is the fourth one. All of these are connected in this way. These are points A and points B. Right? Now, the second one from this is joined to this one. Okay. All right. Cool. Okay. Let me remake this one. Let's do one thing. We'll take a simpler circuit which has an application of this, which should perhaps be a better choice right now, where I am intending to make things clearer for all of you, right? Okay. But of course, you can go back and try this question out. Let me know if there are any queries, right? Okay. So here is the question, IEEE, because that would have taken a lot of time, whereas I am planning to save my and your time in this series, right? In order to give you the concept clarification, that is the aim, by the use of questions, right? Okay, so here you have point A, which is connected to a NAND gate. You have another point B, which is connected to another NAND gate. Okay, both of them are yet connected to one more NAND gate. Both of them are yet connected to one more NAND gate. Okay, yeah, this is the pattern. Now we need to find out what kind of gate this is. Is it OR, NOT, XOR, or NAND gate? Okay, so we have four options: A, B, C, or D, right? Very simple, very easy. Look at the question. Look at the question carefully, right? So let us try to draw the truth table for it. This is A, this is B, and let's say first, what happens when we are taking this one? See here, what happens when we are taking two circuits, let's say 1 and 1, right? Both of them AND will give you 1, and then you're doing the NOT of it by this 0, right? So it means this NAND gate is actually acting like a NOT gate, right? NOT gate. So first you are using A, right? And then converting into a NOT. So here it becomes A naught or A dash. Here B becomes a B dash. A dash and B dash are again being exposed to a NAND gate, correct? A NAND gate. And that is what is giving you X value. So A and B, right? They are both told to become a NAND, right? Correct. So let's try to draw this in the, or basically let's try to solve this by algebraic method. So we have A turning to not, then B turning to not, and sign in between, and then both of them made a not together. See here, this is first and then a dot, which is representing the NAND gate in total. Correct? Now we know one rule: break the line, change the sign. Break the line, change the sign. Break the line, change the sign. Let's do this. This is the rule of solving such questions. Okay, change the sign. Very simple, right? Now I have broken the line, and now see, I'm changing the sign. Can you see this? See it very carefully, right? See, this line has been broken amongst A dash and B dash, right? And this sign has changed from dot to plus and to or, right? You must be wondering, why have I written this A dash here and B dash here? See, this is not, symbol of not. Similarly, this A dash can also be represented by A bar. Both are used to present the not terms, right? A not or B not, right? I hope that is clear. Now, not of not will give you the terms. They will cancel out each other. Oh, ho, this is so simple. That means X was nothing but A or B, right? This is A or B. Great. Excellent. Very good. So, you have option A as your answer. Great class. So happy that you all have understood this well. So these were some particular questions that we took from this chapter. Of course, there are some formulas that you will require when you solve questions related to transistors, right? Should they come in your exam. So you might wish to revise those formulas, right? Specifically these formulas. So I will write them down here for your convenience, for your ease. You might refer them back, solve some more questions, and get back to me wherever you have any queries. You can always contact me, right, by commenting on the YouTube videos where these will be uploaded, right? So some of the important formulas or concepts you might require are given as under, correct? Okay, so one of the formulas is the relation between current gain, right? Current gain in a common base and a common amplifier circuit, transistor, that right? So beta is equal to alpha upon 1 minus alpha, where what is alpha and what is beta? Beta is the current gain in a common emitter, in a common emitter transistor, whereas alpha is the current gain in the common base transistor. Both are current gains. So we have a relation between current gain. You know, many students ask me that, sir, how do we define beta? So current gain is basically the output current, right? The output current upon the input current. So output current is IC, right? Input current will be IE, correct? IC by IE. Similarly, alpha will also be, tell me how much. In fact, I think I have drawn, let me check this. Okay, IC by IE, right? Let me check this once again. Give me a second. Yes, yes. So we'll have small shift. This is IC by IB, right? Whereas you can call this for common base, while this one for common emitter. right? Beta is for base. You might wish to remember it that way. Small correction here, right? This is current gain for common emitter. This is current gain for common base, right? Now this can be written as IC by IE, right? Alpha is IC by IE, whereas beta is IC by IB. I hope this is clear to all of you. A very fruitful definition which might turn to help all of you. Please remember that these are alpha and beta are current gains. Similarly, you have a concept called as voltage gain, right? Voltage gain, which is given as voltage gain, which is given as output voltage upon input voltage, and therefore you have the value as beta times of R out by R in. Similarly, see, I am writing all of this. Of course, you must have understood that for a common base, right? Common base understanding, right? So common base arrangement. Similarly, you have power gain. You have power gain is given as beta square whole into R output upon R input, right? I hope the concepts are clear to all of you, right? So similarly, in this chapter, you have different logic gates, right? Or, and, not, etc., etc. I hope you all are well versed with it. Any queries, you might very easily refer your NCERT, right? Good amount of description in the book, right? And, or, not, etc. And several gates. If you put a not here, this will become an and, this will become an or, and so forth, right? So thank you very much, class. Thanks a lot for attending this small session where we have seen questions and concepts from the chapter semiconductors, which might pop up in your exam. So thank you very much for being a part of this course. I am so glad that I could be of help to all of you, right? Thanks a lot. Stay in touch. We have a great number of and excellent quality videos coming up on this channel, Physics with Fatnani. So stay tuned. Thank you very much for being a part of this course. I wish you all the luck. My prayers and blessings are always there with you. May God bless. Thank you.